Hey guys, welcome back to my channel. So in today's video, we'll talk about linear multiclass classification. So in the last video, we talked about linear classification where the output was a binary classification problem where either you can get class 1 or class 0 as the output, and we only had two classes in our data points. Now what if you have multiple classes that you want to classify your data into, right? So for example, here we see that there are 4 classes and we want to predict whether a new data point belongs to what 4 of these classes, right? So let us start by a definition of linear multiclass classification. So it is basically a type of machine learning algorithm and it is used to classify data into more than two classes. It is an extension naturally of the binary linear classification problem, which uses a straight line to separate the data into two classes, which we have seen in the last video. In linear multiclass classification, the algorithm tries to find a linear function that separates the data into multiple classes. So it comes up with a linear function that can separate data into multiple classes, and which we will see in detail. And this function is actually represented by a weighted sum of the input features where each weight corresponds to a specific class, right? So for example, this is our problem statement. What we have to do is we have different kind of shapes and we want to classify data points into 4 shapes: square, triangle, circle, or a trapezium. So each of this has each of them is a separate class, and each of them have a separate weight vector also, right? So we have the weight vectors equal to the number of classes basically, right? So we have 4 weight vectors, and what basically linear multiclass classification does is that for any of this one weight vector, the output or the prediction will be the highest, and we will say that for that output or for that class, this point basically belongs to that particular class, right? So this is how it would look if you plot those points, right? This is how it would look diagrammatically. So there are 4 classes. This is a place this point is actually controlled by the bias parameter that we have. So we have discussed that there are 2 parameters in the linear equation. One is the weight and one is the bias. So bias in this case controls where these group of weight vectors will actually be positioned in the coordinate space, and then each weight vector has its own direction. So now if your point is or weight vector 1 is more prominent for your input point, that would mean that your data point belongs to the triangle class, right? So this is how you come up with classifications of whether a data point belongs to class 1, 2, 3 or class 4. So this is the setup of linear multiclass classification. Now let us look at the formal definition of what linear multiclass classification is, and I just want to reiterate that this is the theory part. We'll cover the implementation part also in the second part of this video, where we'll code linear multiclass classification problem in Python. So let us understand the formal definition. So here again the input is a tensor, which is a d-dimensional tensor similar to linear classification. Now here label can be anything from 0 to k minus 1, then where k is the total number of classes, right? So instead of just being 2 labels possible, 0 or 1, now you have k minus 1 label or k label possibles total. That could be a prediction of your model, right? Now so again, if you have k predictions, so parameters also change. Earlier weight vector was a vector of d dimension or vector equal to the dimension of the input. Now your weight vector will be of d cross k dimensions. Basically what that means is that each weight vector will be of d dimensions and there will be k such weight vectors, right? And k such weight vectors where k is equal to the number of classes that you have on which you want to predict, right? And then bias. So bias again, instead of being just a single real value, it will now be a real value with k dimensions, one for each of the class that you want to predict for. So let us take a small example. So for example, if you have 4 classes, right? So I'll say that you have class 1, class 2, class 3 and class 4. So what will happen is now you will have 4 weight vectors which will be of d cross k dimension. So what that means is that there will be one weight vector like this, w1, then w2, w3, w4, right? So you will have 4 weight vectors, right? Now each weight vector represents each of your class, right? And each of it is of d dimension, right? So here basically you can either say D cross K, or you can also say it to be K cross D, which is the same thing. It just basically change when you do the transpose and try to do the calculations. But basically the idea of the I dimensions here is that you have K weight vectors. Each weight vector is equal to the dimension of each weight vector is equal to the dimension of your input vector. So now when you will do, so now you have these weight vectors, and now when you will have an input, right? So input will be of D dimension. So what you'll do is the equation again here is Wt into X plus bias, right? And then bias again is for individual class you have separate biases. So you will have a bias for each of the separate classes, right? So now when you will do when you do the calculation, what you'll do is you will multiply the input vector with the weight vector. So W1 into input 1 plus B1, W2 into and W4 into I1 plus B4. So this is how you will do. You will do the calculation. Basically what this equation says is that you multiply the input vector in the entire matrix, right? So the input vector will be multiplied with all the weight vectors and will be adjusted for all the biases, right? And then you will have your, so if you simplify this, what you'll have is you'll have prediction. Let us call this your Y1 prediction, Y2 prediction, Y4 prediction. So you'll have an array of your predictions which is equal to the number of classes. Now essentially what we want to do here is that for the class which has the maximum value, for which the weight into input plus bias is the most pronounced, right, or is the most highest, we want to say that that input belongs to that class, right? That class is the most suitable classification for that input point. So we basically want to do is we want to just do an argmax of this array, right, is this vector. But similar to what we discussed in linear classification, Rmax is a very strict condition, right? We don't want to be that strict that just by, if it is just a small change or a very less change, we do not want to make it a very hard condition, just like in linear classification where we avoided greater than 0 check. Here we avoid the argmax check. Rather we use a softer check which is called the softmax function. So softmax function, what it does is, we'll discuss it in detail in the next segment of this video, but what basically it does is it converts these numbers into probabilities. So what softmax will do is, softmax basically what it will do, let me clear this out. So what softmax will do, it will basically convert this into a array of, or rather, let me write it like this, soft max of y1, y2, y3, y4 will actually give you an array of probabilities, right? So this will give you an array of probabilities. So softmax converts a vector into a vector of probabilities where each probability ranges from 0 to 1 and the sum of the vector is 1, right? So this is why we use softmax, because it's a software version of argmax, and this seems to work well in practice. That is why softmax is used. So that is how your prediction is done. And then loss is the same. It's the negative log likelihood of the probability. Instead of your prediction, it is the negative log likelihood of the probability. So this is the same, and the optimization for this we have already seen. So this is the definition of your linear multiclass classification. It is just an extension of binary classification where you just had 2 classes. Now you can have k classes, and to support that you have equal number of weight vectors and equal number of biases, and for whatever weight vector and bias combination your probability of that is the highest, you basically classify that input point for that particular class. Okay, so now only thing that we haven't discussed here is the softmax function. So now let us understand softmax function in detail. It is a very important function, and you will see it being used throughout deep learning, and when we go into more advanced topics of deep neural networks or neural networks in general, you will see softmax being used at a lot of places. So let us understand it in depth right now only. So Softmax is a mathematical function that is used to convert a vector of real numbers into a probability distribution. So any vector of d dimensions is basically converted to a probability distribution. Every number in that vector is converted to a number from 0 to 1, which is a probability, and the sum of all those probabilities is always 1. That is how we know it's a probability distribution. It is commonly used in machine learning for classification tasks. So this is a very common use case of softmax function, which is classification, because that is where, when you have x number of outputs to choose from, then you want to see which is the most probable output, and then you want to place your bet on that output, right? So that is why it is used in classification tasks, where output represents the probability of each class. So this is basically what we have discussed in the formal definition part. So now softmax function takes a vector of real numbers as input and returns a vector of the same dimension, with each element being a probability from 0 to 1. So this is something we already discussed. How is softmax function defined? So this is basically the definition of softmax function, right? So what it does, let us understand very quickly. For every value in the input vector x, what it does is it raises that value to the power of, as a power of exponent, and divides that with the normalized value, right? So this basically is just raising the power of that, whatever you have as the value of that vector at ith position, raising it to e, and below is the, for the entire vector, it is the sum of that values, right? So every value raised to e, when you add it, that becomes your the denominator of this equation. Now why is this being done? So there are two things that are being done here. One is that the value is being raised to the power of e, and then it is being divided by the sum of all the values raised to the power of e. So why is that done? So the reason why we have exponent here is basically because it has the effect of amplifying large values and suppressing small values. That is why we sort of use the exponential power, right? Why we raise it to the exponential power. And the normalization here is, so this is the reason of why it is being sort of done as an exponential power, and the exponential values are then normalized so they would sum to 1, right? And that is why it is being divided with the normalized value, which is the sum, right? So the reason why this is done is because so that every value, then when you sum it, so let us assume there are just two values, so I is equals to 2, right? So what it will become, so if we say softmax of x1 plus softmax of x2, let's try to do this, right? So these are probabilities, so ideally it should always sum to 1, right? So now let us see whether they are summing to 1. So it's a very quick calculation just to show why we are normalizing it. So it will be this ex1 plus ex2, ex2, ex1 plus ex2. This will basically become ex1 plus this, just one second. So this will be ex1 plus ex2 upon ex1 plus ex2, which is basically nothing but your 1, right? So that is why we are normalizing it, so that they actually turn into probabilities, right? Because we have to use them as probabilities. And so again, yeah, this is also telling that this ensures that the output value represents a valid probability distribution. So that is why we normalize it. Now this is a very simple thing, but this basically helps you to understand that how each class, or how confident is your model for each of the classes, right? So let us see for an example. Now you have an example, you have an input vector of 2, 3 and 1. Now if you see, these values are not that separate, right? There is just a difference of 1 with each of the values. But when you do a softmax on this becomes the output, right? So the highest value is a very prominent effect. It has a 66% probability, right? And the lowest value has just a 9% probability. So although that difference was not visible in the actual values, the softmax amplifies those differences and suppresses the small value, so that those differences are very prominent for your model to understand and learn from, right? So that is why softmax is a very good function. Another thing is that if your softmax distribution has multiple values, if you increase the value of any one of this any one of this parameter. For example, if you increase the value of any one of the class, so rest of the classes automatically will shrink, right? So it basically automatically will shrink, and the class that you have increased will increase. So basically it maintains the balance across all classes, and your so that the sum always is maintained to 1. So this is a very good property that softmax function has, and that is why it finds a lot of use in throughout machine learning. Okay, so I think that was it. This is what I wanted to discuss in this video. We discussed linear multiclass classification. We saw that how is it different from binary classification, because it has multiple classes in which you can classify your input points. We also saw how softmax function is used not only in this, but how it will be used even in future topics that we'll discuss, where you have a classification across multiple labels and you want to use a probabilistic classification, and then depending on just the actual values of the vector. So that is why it is very important. Thank you so much for watching this video. Please do not forget to like, share and subscribe. And in the next part of this video, we'll talk about the coding part of linear multiclass classification. So do not forget to look for that video.